Hello, welcome to my M1 in 30 minutes revision video. Before we start, I want to talk about the general structure of solving a mechanics problem. Step 1. Make sure you read the question carefully. Later, we'll see how important information can be tucked away inside the question. 2. Draw a visual representation of the problem. This is part of the process of understanding the problem, and it collects all of your key data inside your view. 3. Apply the laws of mechanics to create equations. You'll need to decide which laws are applicable. And then finally, you solve the equations to answer the questions asked using standard mathematics. I'm going to focus on the first 3 steps. Let's move immediately to look at some problems which might be set. We'll start with the kinematics question. The particle P is projected vertically upwards from a point A with speed u meters per second. The point A is 7.5 meters above horizontal ground. The particle P moves freely under gravity until it reaches the ground with speed 28 meters per second. You have to show that u is 21. Now, before we look at diagramming the question, let's just recall the basic SUVAT formulae. The first one, V equals U plus AT, is easy to remember because in each unit time the velocity will increase by A, the acceleration. The second formula, S is a half U plus V times T. A half U plus V is the average velocity, so the distance travelled is the average velocity times time. The remaining 3 can be created simply by eliminating one of the 3 variables from the 2 equations. Eliminating T, we get V squared equals U squared plus 2AS. Eliminating V, we get S equals UT plus a half AT squared. And finally, eliminating U, we get S equals VT minus a half AT squared. You need to remember these as they're not provided in the formula book. And often I think it's a good idea to jot down those equations when you come across your kinematics question so that you can refer to them directly. Now back to the question. Here's a picture which represents the problem we have to solve. We've got a point A, 17.5 meters off the ground. The particle projected at velocity u hits the ground with velocity 28 meters per second. Now, it's operating freely under gravity, so that the acceleration will be 9.8 meters per second squared in the downwards direction. We have to choose a positive and negative direction, and by convention I'm choosing positive to be the upwards direction. So now we need to work out u. We know the distance, which will be minus 17.5 meters. We know the velocity v, which will be minus 28 meters per second, and we know the acceleration, minus 9.8 meters per second. So we use v equals u squared plus 2as, and we create this equation, which is easily solvable in terms of u. In fact, u can be 21 or minus 21, as we get an equation in u squared. So 21 is the velocity when projected upwards, and minus 21 is the velocity at this point here when it reaches the same level coming downwards. Okay, let's move on to the second part of the question. It says at time t after projection, P is 19 meters above A. Find the possible values of t. So, in some cases we'd need to draw a fresh diagram. In this case, we can still use the original diagram. So, we draw a line across here showing 19 meters above the point A, and we can see as the particle rises, it will cross the 19 meter mark, and then at some time later it will cross it again. So we're expecting two values of t. We know u is 21, so we can now use this equation, s equals ut plus a half at squared. So we substitute the values into this equation, and we have 19 equals 21, which is the u times t, plus a half. Acceleration a, remember it's negative, minus 9.8 times t squared. And this yields us a quadratic in t squared, which will give us the two values of t, where the particle is 19 meters above a. You'll solve that with the formula. Okay, let's move on to momentum. Here's our question. We're going to read the question and we're going to create an appropriate diagram. So we have two particles A and B of mass 5m kilograms, 2m kilograms respectively, moving in opposite directions on a straight line. The particles collide directly. Immediately before the collision, the speeds of A and B are 3 and 4 respectively. So here we have a situation described diagrammatically. Finally, it says the direction of motion of A is unchanged by the collision, and immediately after the collision the speed of A is 0.8 meters per second. So here's the picture after the collision. The mechanical rule that we need to apply is the conservation of momentum. So we need to remember that direction matters for momentum. The momentum of particle A is 3 times 5m. The momentum of particle B is minus 4 times 2m, because it's in the negative direction. After the event, the momentum of A is 0.8 times 5m, and we add v times 2m. Okay, that gives us an equation in v, which is straightforward to solve, and we get v equals 1.5 meters per second. Let's look at the second part of the question. It says, in the collision, the magnitude of the impulse exerted on A by B is 3.3 Newton seconds. Find the value of m. Now, when two particles collide, they both exert an equal and opposite impulse on one another. The impulse I on A, okay, reduces the momentum of particle A. The impulse I on B increases the momentum of B. The impulses are the same, and the increases and decreases in momentum are the same, which is why, finally, the momentum's conserved. So, let's see what happens when we look at the change of momentum of A. So we write the impulse, I. Now, we're told the magnitude is 3.3, it's going in the negative direction on A, so we write minus 3.3 for the impulse, and then the change in momentum. So we take the momentum after, which is 5m times 0.8, and we subtract the momentum before, which is 3 times 5m. So we solve that equation, and we can find m is 0.3. Let's look at a dynamics question. Two particles, P and Q, have masses 0.3 kilograms and m kilograms respectively. So we mark that on the diagram. The string passes over a smooth pulley that is fixed at the top of a plane. The plane is inclined to the horizontal at an angle of alpha, where tan alpha is 3/4. So immediately we draw a little triangle, a right angled triangle with alpha. The tan alpha is 3/4. We can work out the hypotenuse, and now we have a simple triangle where we can read any of the trig ratios of alpha. The coefficient of friction between P and the plane is 1/2. So we Draw that on the diagram too. Okay. The particle P is held at rest on the inclined plane, and the particle Q hangs freely below the pulley with the string taut. The system's released and Q accelerates vertically downwards at 1.4 meters per second squared. As the string is inextensible, we know that P will be accelerating up the slope at the same acceleration as Q is dropping. Let's now add the forces to the diagram. So we add the weights of the two particles. So we multiply the mass by G to give the weights. There will be a normal reaction of P to the plane, so we add the reaction. There'll be tension in the inextensible string. The string's going over a smooth pulley, and so the tension in both parts of the string are the same. And finally, we add the friction. And as this is limiting friction, the friction will equal mu, or a half, times the normal reaction, R. We'll resolve the forces on P perpendicular to the plane, and by doing that we see that R must equal 0.3 G times cos of alpha. And then we apply F equals ma along the plane for P and vertically for Q. So for P, the net force acting on the particle P up the plane is T minus 0.5, which is the coefficient of friction, times R, minus 0.3 times 9.8, which is G, times sine alpha. And that's going to equal the mass times acceleration. So it equals the mass, 0.3, times the acceleration of P, which is 1.4. Secondly, we can apply F equals ma to Q. The net force on Q is mg minus T acting downwards. And this is making the mass m accelerate at 1.4 meters per second squared. So now we have three equations, and it allows us to solve for the reaction, which we have directly here, and it allows us to calculate the tension in the string. Let's move on to another dynamics question. This isn't on an inclined plane. Here we have two particles, 0.3 kilograms, 0.5 kilograms, joined by a light horizontal rod. The system of the particles and the rod is at rest on a horizontal plane. At time t equals 0, a constant force F of magnitude 4 newtons is applied to Q in the direction PQ, as shown in the diagram. The system moves under the action of this force until t equals 6 seconds. During the motion, the resistance to the motion of P has a constant magnitude 1, and the resistance to the motion of Q has a constant magnitude 2 newtons. Let's draw those onto the diagram. Drawing the forces, there'll be a tension in the rod, and mark an acceleration. So we'll assume that it's accelerating at a meters per second. And clearly, as the particles are connected by the horizontal rod, they'll both be accelerating at the same rate. Okay. What are we asked to find? Firstly, find the acceleration of the particles as the system moves under the action of F. Secondly, the speed of the particles at time t equals 6. Well, the speed of the particles at t equals 6 will be very straightforward, because it will simply be 6a. And then we need to work out the tension in the rod as the system moves under the action of F. So, which laws will we apply? Well, we'll apply F equals ma again. And what I'm going to do here is apply it once at P and once at Q. So applying F equals ma at P, the net force on P is T minus 1, and it's causing the mass 0.3 to accelerate at A meters per second squared. Applying the same at Q, the net force here is 4, which is the force F, and subtracted from that is T and 2. And that causes the mass of 0.5 kilograms to accelerate at the rate of A, so we get this equation. If we add the two equations together, we get 4 minus 1 minus 2 equals 0.3 plus 0.5A. And this is in fact the result of applying F equals ma to the system as a whole. With these equations, we can easily calculate A. Equation 3 is the best to work out A, and then we can work out T from either of the two remaining equations. Let's look at some statics. A box of mass 5 kilograms lies on a rough plane inclined at 30 degrees to the horizontal. The box is held in equilibrium by a horizontal force of mass 20 newtons, as shown above. The force acts in a vertical plane containing the line of greatest slope of the inclined plane. So, let's add the forces to the diagram. What forces do we have? Firstly, we know the mass and therefore the weight of the particle. We know there's a reaction normal to the plane. Finally, we need to add friction. The question that one has to ask is, will the friction act up the plane or down the plane? With the information given, there's no way of telling. But when we read on in the question, we're told the box is in equilibrium on the point of moving down the plane. This tells us that the friction must be pulling the particle up the plane. If the box was in equilibrium and at the point of moving up the plane, friction would be acting downwards. In this instance, it'll be acting upwards. And as it's limiting friction, because it's on the point of moving down the plane, it will be mu r. What's the question? We have to find mu and we have to find r. As before, we know that because the particle is in equilibrium, the net forces will be 0. So if we resolve the forces at right angles to the plane and along the plane, they will balance. So resolving at right angles to the plane, we can see that r equals 5g cos theta. That's the component of the weight at right angles to the plane. We also have to add 20 cos 60. That is the component of the horizontal force which is acting at right angles to the plane. Secondly, we resolve along the plane. When we resolve along the plane, balancing rg cos 60, that's the weight of the particle being pulled down the plane, there's 20 cos 30, that's the component of the horizontal force, plus mu r, the friction. So we now have two equations in mu and r, and therefore we can solve for mu and r. So that's the end of that question. Sometimes a statics question may be expressed in terms of vectors. In this question, we're given three forces F1, 2 and 3 acting on a particle P that's in equilibrium. We're asked to find the values of little p and little q. First, we rewrite the vectors. Then, as the particle is in equilibrium, we know that the sum of the three vectors must be 0. So we add F1, F2 and F3. We collect together the I components and J components, and the resultant force has to be a vector 0. From this we can easily see that P must be minus 12 and Q must be 4. Moving on to the next part of the question. This says F3 is removed and the resultant of F1 and F2 is R. So R is F1 plus F2. We add the I's and J components and we find that R must be 12I minus 4J. Let's draw a diagram. We have the J direction heading north, the I direction in the direction of the x-axis heading east. The vector 12I minus 4J, and I've marked it as making an angle alpha with the negative y-axis. So in this picture we can see that the magnitude of the vector 12I minus 4J is calculated using Pythagoras, so it's the square root of 12 squared plus 4 squared. So tan alpha equals 12 over 4 equal to 3. From this we can calculate the angle alpha is 71.6 degrees by using the inverse tangent. And so the angle that the vector 12I minus 4J makes with the direction J is going to be 180 minus 71.6 equals 108.4 degrees. Now let's look at a moments question. Here we have a non-uniform rod AB of mass m and length 5d resting horizontally in equilibrium on two supports C and D, where AC equals dB equals little d, as shown in the diagram. The centre of mass of the rod is at the point G. Notice, because it is a non-uniform rod, then the centre of mass isn't at the midpoint of AB, it's rather at the point G. Then we're told a particle of mass 5 over 2 m is placed on the rod at B, and the rod is on the point of tipping about D. We've got to show that GD equals 5 over 2D. Let's mark on the forces. We have the mass of the rod, we have the mass of the particle put at B, and we have reactions at C and D. As the rod is on the point of tipping about D, that tells us that the reaction at C must be 0. Now, what mechanics should we use? As the rod is in equilibrium, we can take moments about any point, and the resultant of all the moments should be 0. Where should we take moments? Here, as we're looking to find the distance KD of G from D, the best place to take moments is about D. The reaction R2 is unknown, but if we're taking moments about D, the value of that reaction is not important. So we take moments about D, we get KD times mg, the mass of the rod, and that's got to balance with D times 2.5 mg, which is the mass of the particle at the point B. So from this it's clear that GD equals 5 over 2D. Let's look at the second part of the question. The particle is moved from B to the midpoint of the rod, and the rod remains in equilibrium. Find the magnitude of the normal reaction at the support D and the rod. As we've moved the mass from B to the midpoint, the reaction at C will no longer be 0. So we have separate reactions at C and D. To find the reaction at D, we'll take moments about C. We don't know the value of the reaction R1 at C, but taking moments about C means that this isn't important. Here's our resulting equation. 3dR2, that's the moment anticlockwise of the reaction at D. That's got to equal 0.5d mg, that's the moment of the weight, plus 1.5d times 2.5 mg, that's the moment of the additional mass. From this equation, it's straightforward to calculate the reaction R2 at D. Okay, let's move on to the last question. This is a vectors question. We're told two ships P and Q are moving with constant velocities. Ship P moves with velocity 2i minus 3j kilometers per hour, and ship Q moves with velocity 3i plus 4j kilometers per hour. We're asked to find, to the nearest degree, the bearing on which Q is moving. Now for Q, we'll draw a picture to represent the vector. Here's the velocity of Q. It makes a 3, 4, 5 right angled triangle. So we can calculate the angle alpha that the vector VQ makes with the j direction or the north direction. Recall that the bearing is the anti-clockwise angle measured from the north direction. So here it's straightforward to calculate alpha as 0.37 degrees. Again, recall that a bearing is conventionally written as. For the next step, at 2 p.m, ship P is at the point with position vector I plus j kilometres, and ship Q is at the point with position vector minus 2j kilometres. Let's write that as P0 equals I plus j, Q0 equals minus 2j. At time t hours after 2 p.m, P and Q will have new position vectors. We have to write down expressions in terms of t for these vectors. So P will be I plus j, its position vector at time t equals 0, plus t times 2i minus 3j, its velocity vector. We can simplify that by collecting the I and j terms together to have P equals 1 plus 2t i's plus 1 minus 3t j's. Similarly for Q. Q is minus 2j, that's its position when t equals 0, plus 3i plus 4j times t. We reorganise that equation in the same way, so that Q equals 3ti plus minus 2 plus 4tj. We can calculate the position vector of P and Q at any time t hours. Part 3. We're also asked to write down an expression for PQ. Before we do that, let's just recall. If P has position vector little p, Q has position vector little q, to work out the vector PQ, we use the triangle of forces. If we start at P and we move to Q, we have to have minus P plus Q, or Q minus P. It's important to remember that PQ is actually Q minus P. With that information, we can easily calculate the vector PQ from the expressions that we have for P and Q above. So PQ equals Q minus P. We subtract the vectors and we get that PQ is T minus 1I plus 7T minus 3J. The final part of the question asks when Q is due north of P. Well, if Q is due north of P, then PQ will not have an I component. PQ will be purely expressible in terms of J's. So that tells us that to make the I component 0, we simply set T equal to 1. So T equals 1, that's 1 hour after 2 p.m. So T equals 1 or 3 p.m. would be a valid answer. Part 2. We have to calculate the time when Q is northwest of P. So we take the vector PQ and we put it equal to lambda times I plus j. This is because I plus j is a vector in the northwesterly direction, and if PQ is pointing in the northwesterly direction, PQ must be parallel to IJ, and so it's a scalar multiple of IJ. To solve this equation, we simply have to work out the value of T when the I and J components of PQ are the same. So we work out the value of T when T minus 1 is the same as 7T minus 3. This gives us T equals 1/3. 1/3 of an hour is 20 minutes. So as T equals 0 is 2 p.m, T equals 1/3 is equivalent to 2:20 p.m. That concludes my M1 in 30 minutes video. I hope you found it useful.